Okay, let's continue with the next one. Now, all of these, this little tip is going to be useful here, where it talks about if you're taking limits involving, this means plus or negative infinity, and the numerator and denominator are both polynomials. That means this is a rational function. That's what we call this in algebra, rational function. If it's a polynomial over polynomial, you really only care about the biggest degree. So I'm going to highlight those each time. Biggest degree here is 4. The biggest degree here is also 4. Whenever your degrees are perfectly the same, you're going to be able to do a little trick to find the limit as x approaches infinity. You take the quotient of the coefficients. So these are both 4. So here's the thing. Here's what I care about. I actually do care about the 2 and the 8, and it's the quotient of the coefficients. You get 2 over 8, which simplifies to 1/4. You can confirm that on your calculator if you want. You can graph this big, complicated thing, and you can plug in a really, really, really big x value. I guarantee you your y value that it'll spit out is going to be really, really close to 0.25. It might be 0.24. It might be 0.26. But if you go far enough to the right, it's going to be 0.25, like almost, especially if you're rounded, right? So, but we don't need to do that with the calculator. We can just use intuition here. And you can confirm that if you want. So let's look at the next one. Let's look at we only care about the biggest powers. I'm going to be very careful. Make sure these things are in descending order. You notice these are in descending order, so we're okay there. So we have that one's, there's a 4, there's a 2. Powers do go down. Now, when the power on the top is bigger, it's going to grow so much faster as x approaches infinity, so it's going to dominate. But whenever that happens, your limit is just going to go to infinity because this thing behaves, if you take x to the fourth divided by x to the squared, it behaves like an x squared. And since we're approaching positive infinity, x squared, if you take the function x squared, it goes to positive infinity, so it's gonna go to positive infinity there. So this one is positive infinity. Let's look at this one right here. Notice how it's the same function, but let's find the limit as x approaches negative infinity. Well, this thing is still like an x fourth over x to the second, so we're still looking at just this 4 and just this 2. That's really what we care about. So what we're going to do is now we as approaches negative infinity. Well, here's the thing. The end behavior on both sides is the same on these. End behavior is the same because it's a parabola, even function. So even as you approach like a super, super, super far negative value, it'll still go up to infinity, right? Even though I'm taking it as x approaches negative infinity. Now, an odd function won't do that. So you have to be careful. If for some reason, like say this were a 4, and let's say you had for some reason you had like a cube right here. Well, that would be, so let's just scratch that out and edit it, pretend like that was like a third power. Okay, so let's put x to the third power right there. If it would simplify into x fourth over x to the third, so it would come out to, and let me show my pen here, x to the first power. Well, x to the first power behaves a little bit differently. As you approach positive infinity, yeah, it goes up and to the right, so the answer would be infinity. But if for some reason you got an odd power as your end result, as x approaches negative infinity, the result would be negative infinity. So be careful. Make sure your result, look at whether it's an even or an odd function. Now this is one. It kind of looks like the same, like kind of looks like what I edited this to. But here's the problem: this one's not in descending order. You got to be careful. Make sure they're in descending order. If they're not, here's what really happens. We only care again about the highest powers when you're looking at these limits as x approaches infinity for these rational functions here. If it's polynomial over polynomial, if you take an x to the fifth and you divide it by an x to the sixth, well, here's what happens. You get a 1 over x. Okay? Now, just kind of plug infinity into that, all right? Now, I'm gonna graph 1 over x. Even if you say what if you say, well, I don't know what the graph of that looks like. Well, let's take 1 and divide it by infinity. Well, you think, oh, I can't divide 1 by infinity. Well, take 1 divided by a really big number. What's 1 divided by a really big number? What's 1 divided by 100? 100th. What's 1 divided by a million? 1 millionth. Right? So it's practically 0. So what happens is um, if ever you get where your top power is bigger than the bottom, you'll notice it goes to either infinity or negative infinity if you have an odd value. But if your bottom power, like the 6, is bigger than your top highest power, the 5, it's going to go to 0. But if your powers tie, right, if your highest degrees, your highest powers tie for these polynomials, it will be the quotient of the coefficients. So that's a good little rule, and you don't have to memorize that. You can just use your intuition. But if you want to memorize it, great. Now let's look at these just to fire off some that are really easy. Limit as x approaches infinity of 1 over x. You really should know what this graph looks like. This graph looks like that. Okay. Now 1 divided by infinity, 1 divided a really big number. Here's the thing, it goes to 0. Or graphically, take x as I take really big x values. That means I'm going further and further to the right here. And so as you go bigger and bigger x values, you'll notice the y values get really, really small. You can confirm that if you use the trace function on your calculator, or you could just use tables. Look at negative infinity. See how the same thing happens? Same thing happens as you go to negative infinity. You still are dividing 1 by a really big number, even though it's a negative number. So you still get 0 though, because that forms a horizontal asymptote. Now, let's approach 0 from the right. So here, I'm going to look at 0 from the right. Let's go to 0 from the right. That's this part right here. Notice how this thing goes to infinity. And you can think of it this way. If I take, as an example, if I take 1 and I divide it by 0.001, that's 1,000th. So you get 1,000. If you divide it by a millionth, you get a million. If you divide by a number really close to 0, you actually blow numbers up. You don't shrink. So this actually goes to infinity from the right, but if you approach it from the left, watch what happens as you approach from the left. You approach 0 from the left, see how it goes to negative infinity? So this one's going to be negative infinity if you approach from the left. All right, what if we approach 0 in general? Well, the problem is there's a disagreement. As you approach from the right, there's this purple thing right here. They're saying, obviously it goes to infinity. The blue guy who's approaching from the left says, no, it's negative infinity. They disagree. This limit does not exist. Okay? Let's play around with these even a little more. What if you approach 0 from the right, 1 over x, but then you shift the function up by 5? Well, here's the thing. If you compare this to this part right here, well, the only difference is I shifted it up by 5, right? Well, guess what? What's infinity plus 5? Guess what? It's still infinity. So that shift up is not going to make a difference right here, but it might make a difference in another situation. Let's look at this. The same thing as a downshift, approaching the life. It's not going to make a difference. You're still going to have a limit of infinity. You can confirm that graphically, right? But let's look at it as x approaches infinity of 1 over x plus 5. Here's what that function looks like. It's the same shape, the 1 over x, but I'm going to shift it up by 5, so it'll look more like this, right? So we have the same vertical asymptote, but the horizontal asymptote, instead of being on the y-axis, it's shifted up by 5. So you can compare this to that very first question right here. Instead of having a limit of 0, it's a limit. The limit value is 0, but shifted up by 5. 0 plus 5 is 5. As you approach negative infinity, the negative doesn't really matter because it still has a horizontal asymptote, the negative infinity, but the minus 3 is a downshift. That one's going to be minus 3. All right, and this one is actually a repeat of an earlier one, so we can actually ignore this. But it's good to know that when the shifts matter and when they don't. So a vertical shift is going to matter as you're approaching infinity, but the vertical shift doesn't matter when you're approaching 0. In the same way, if we did a horizontal shift, so let's say we did a horizontal shift of this one as x approaches 0. Let's do 1. Let's just change this to 1 over x plus 4. That's actually a shift to the left. Normally, like 1 over x plus 4, what it's actually going to do is going to change where the vertical asymptote is. So it's going to make it to where you could actually plug 0 into this function if you want. You get 1 over 0 plus 4. So this will actually normally, if you're taking the limit as x approaches 0, normally you think, oh, you can't do that, but you can do it here because that actually is in the domain. All right, last few we'll look at. We'll look at these in a second.